Okay, good morning everyone. Welcome to the one problem one day per day problem. These are set of problems which are coined from 9th to 13th December. That is from tomorrow onwards will be published. Okay, so let us look at the first question. Question number 1. A mass spring oscillates horizontally. Let me start it. This is for 10 marks. So I allotted 10 minutes for this. Okay, now a mass spring oscillates horizontally on a frictionless surface. The mass has an acceleration a when it is displacement from its equilibrium position is x. Okay, so you have a mass spring system. Is the diagram given? Okay, no. So horizontally on a frictionless surface. It means what? So this is my spring. This is the object over here. It's oscillating about a frictionless surface. Acceleration a when it is displacement from its equilibrium position is x. Okay. The variation of a with x is modeled in two ways, a and b, by the graph shown. So it has been modeled like this. Let us understand the graph first before proceeding further. So you see this is graph a, which shows you that acceleration is proportional to the displacement. You see there is a straight line and passing through the origin. The second graph shows you until this particular region. Where is it? Until this region and this region here, maybe around 0.04, I observe that acceleration is proportional to displacement, and after that it deviates. Of course, acceleration is proportional to displacement, but it's not linear in nature. It is non-linear in nature. Okay, one is a linear graph, the other one is a non-linear graph. Okay, next, outline two reasons why both the models predict that the motion is simple harmonic when a is small. What do you mean by a is small? See, this region determines a is large. A is large, right? Here until here a is large, and here a is small. So this region is also a is small. This region is also a is small. So a is small. Okay, so therefore, if you consider this box over here, a is definitely small and it is seen to be proportional to the displacement. So you need to put across two reasons. What are the reasons first? See, you just give the definitions of SHM. What is the definition of SHM? First one is acceleration is proportional to displacement in this region. Both the graphs, both the models predict the same thing. And secondly, direction of acceleration is opposite to direction of displacement. Now you can ask me, how do you understand the direction? Okay, now let us look at this here like this. See, for example, when I say acceleration is negative here, now what is the displacement? Displacement is positive. How do I understand that? Let us say, for example, I take one particular point, this point. What is the value of this point? Minus 0.02. Now draw a line here which intersects this line at this point. What is the value of displacement? This is displacement. What's the acceleration here? Displacement is negative, which is nothing but minus 0.02 meters. And what is the acceleration there? Acceleration there is seen to be around 0.2, 0.4, 0.6. This is seen to be around 0.6 meter per second square. Okay, you see, when one is positive, other is negative, which means what? Say the directions are negative over here. Of course, the magnitude wise, as this increases, this also increases. That's what I said, acceleration proportional to displacement, right? So in a similar way, if you want to verify here also, you can do this. See, when I say the displacement is positive, then what happens to acceleration? Acceleration is negative. So therefore, definitely these two confine within the region of SHM, or this is nothing but it predicts the SHM. Okay, so you get easily 2 marks here. Next, determine the time period of the system when a is small. Determine the time period. Now you know, when we model this one, what is how is acceleration related to displacement? A is equal to minus omega square x. So what we will do is we will take up the slope here. Draw this line here and take up this line over here. We will take up the slope. What is the slope? What does the slope tell you? Slope here is equal to, what is this now? This value is equal to 1 divided by, what is this value here? Minus 0.04. Minus 0.04. When I do this, what is the answer I get? Let us take 1 divided by 0.04 will give me 25. 25. What about the units? So this is acceleration meter per second square, and this is displacement. So this should be 1 by second square. 1 by second square. Now if I take this acceleration by displacement according to equation, what does this give you? Minus omega square. Okay, so minus omega square is what is been represented over here, which is equal to minus 25, right? Minus 25 over here. So what I will do is I will find out the value of omega square from here. So minus omega square equal to minus 25, or omega square is equal to 25, or omega is equal to 5, or t should be equal to 2 pi divided by omega, and I can now substitute this value 2 pi divided by 5. So let us calculate what is this value now, which should now be 2 into 3.14 divided by 5 will be equal to 1.256. 1.256. Now I don't want so many numbers over here. Closer to this is 1.3. Now what is it now? Time period, which is second. What is it being asked? Time period. Time period is 1.3 seconds. We have shown this. Okay. Now next, outline without calculation the change to the time period of the system of the model represented by graph B when A is large. Now what happens to time period in case of graph B? That's main question. Now in graph B, okay. Now what happens to time period? Now you see, we calculated time period from the slope here. Now if I want to calculate the slope, what will happen here? You get one slope here, you get another slope here, you get third slope here, you get fourth slope here, and so on. The slope is continuously changing. If that slope is continuously changing, what should I do? I should take the average slope. Now how do I take the average slope? Should I keep on taking slope, everywhere slope here? No, that's not right. So what we do is, we take, whenever there is an average in a changing circumstance, what you do is, you find out what is this y coordinate, and then find out what is the x coordinate here and what is the x coordinate. Divide one by the other, similar to that of the average velocity or average speed. Now when you do this, what is the y coordinate here? Average y. No, okay, I will not even do the calculation because he said there is no calculation required, outline without calculation, right? Now here what happened was, in case of the graph A, this delta y was larger, right? Now I will write it now like this only. I'll write delta y of A is greater than delta y of B, and what about delta x over here? Delta x I'm going to take, because I'm going to take this full slope over here, right? So therefore, so if I take delta x is same for both the coordinates, delta x remains the same and delta x is same, which means slope which is equal to delta ya divided by delta xa is always greater than, slope a is always greater than slope b. Now what does slope tells you? Let us go back to this once again. What does slope tells you? Slope tells you, where is it? It's here, right? Slope tells you it's omega square. See, I took this value and equated this to omega. So therefore I can now write slope is equal to omega square, which means I can now write omega a square greater than omega b square, which once again means omega a greater than omega b. But since omega is equal to 2 pi divided by t, I can now say Ta is less than Tb, right? In other words, Tb, because we are happy only with greater than symbols, right? Tb is greater than Ta, which means what? This will take, what is he asking? Change to the time period of the system, which means what? The second pendulum shown in graph B, second spring which is shown in the graph B, okay, shows a larger time period. This is what we can say about it. Okay, now let us move on to the next one. The graph shows for model A the variation with x of the elastic potential energy. Stored in the spring. Okay, so it is saying elastic potential energy equal to 0 at the mean position. That's right. Okay, so this is my spring like this. This is how it starts oscillating. Okay, when it is here, this is, let us say for example, this is one extreme, this is other extreme, and this is the mean position. This is the mean position. Okay, this is the mean position here. So this is the mean position here. Okay, so as a result of this, this is a compression, this is an expansion. Now what is it asking? Describe the graph for model B. For model B, what happens? Okay, what is this graph on? This is your EP versus X. Now you look at this first graph here. You see, in this region, the velocity, the acceleration is same. If acceleration or displacement is same, whatever parameters you are going to draw for graph A and graph B are both under the same. Which means what? So A and B are behaving alike until 0.04 meters in displacement. Now let us come back, and therefore until 0.04 or 0.05, until here graph A and graph B will have the same potential energy here. Now after this, two conditions can arise. Maybe does the graph go like this or does the graph go like this? That's what we need to ask. So towards it, how do I know? Now we know that potential energy, how is it given by, this is given by half kx square, right? So half kx square, which should be half m omega square ex square, right? So therefore, this is the potential energy stored in the spring. Now what happens to omega? Now let us look at this once again. Omega A is greater than omega B. That means for graph B, omega B is lesser, right? Omega B is lesser, and as a result of this, now the final potential energy will definitely reduce, which means it will not go until here, but might be it will go until here, it will go until here maybe. Okay, here also it will go until here, which means it cannot converge like this. It has to diverge like this. It has to diverge like this. So this we have drawn the graph. Very simple, okay? Only thing is you need to look at on what parameters each one of them depend. See, what is this parameter on y-axis? It's nothing but EP, potential energy. This potential energy depends upon this omega. Okay, so if it depends on omega, so definitely when omega is lesser for this, what we should do? We should draw a lesser energy. It should get a lesser energy, right? When omega is lesser, EP is lesser, so it should get a lesser energy. That's it. Okay, let us move on to the next one. So this is also done for you. Done. Next one. We close this timer. It was of no use. Oh, we have done with it. Okay, so thank you. Let us see you tomorrow in the next video.